Okay. Okay, we can start. Now we are online.
Okay, so can I go ahead?
Again, Rosario should be.
No, I'm here. Sorry. Okay, so perfect. I'm sorry you probably have been introduced already, but in any case, let me do it once more. So Perfecta is a PhD student from TU Technical University of Eindhoven, and she also works with Acomea. And today she's going to talk about predicting customer investment potential value and application in a fintech company. Thank you, Perfecta.
Okay, thank you for the introduction. Well, Rosario has already stated my topic, so I'll just move to the next slide. Oops. Okay. So the outline of my talk, I will first describe my project, and then I would define the problem and the goal we are supposed to achieve in this project. And I will also describe the app, which is the Gimme 5 app. It's important. This description is important for you to understand the problem we are trying to solve. Then I will go ahead to talk about the model we used in estimating this the individual investment potential of the customers. Then I will also discuss the problem of dimension reduction and the algorithm we have proposed to solve this, and move forward to discuss some metrics we've proposed to segment customers based on the estimated investment potential. And finally, I will show some results. Now, the project is based on an app that is provided by Acomea to its customers. As Professor Alessandra said, Acomea is a company, it's one of the industrial partners for the Big Math project. So let me first give a brief description of the Gimme 5 app. In every aspect of life, we all set goals one way or the other. I think goal setting is an integral part of all of us, be it in work life or our personal life. Now, Gimme 5 app is a digital piggy bank that help investors save small sum of money at a time. And they can use this, it's not just saving, but you invest this saving into equity or bond mutual funds. Now, the app has this goal setting feature where investors are allowed to decompose their savings into different objectives. So like somebody can say, I'm saving towards a trip to Asia, or I'm saving towards my retirement, or I'm saving to buy a car, or for future travel. So you have different types of objectives that you're saving towards, and what you're saving is invested in a mutual fund that you pick. So depending on your risk level, you pick whatever fund you find appropriate and suitable for your risk appetite. So this is just a picture of the app, and the app has this function where you can virtually save, where you don't actually put in money, but you just say, okay, every day I put in €5, and at the end of the month, the company collates or sums up everything that you've virtually saved, and then they ask you to either transfer it or you provide a direct debit access to your account. Now, the goal of okay, let me describe the data. So in the data set, we have some users that deposit as low as 30 cents per month. So it's just like, it's not like somebody actually sends 30 cents, but on the average, if we divide by the number of years somebody has been a customer, we have that people save as little as 30 cents a month, and people can also save as much as 142 euros a month. Okay, and given this, the aim of the project is to identify customers who have their investment potential larger than what they're actually doing. So, for instance, we want to see if customers who are saving 100 euros can actually do more than 100 euros. We try to estimate this investment potential. So what do we have? We have data, we have demographic data, which is about the age, where the person is from, like the country, where the person resides, like what city the person resides in. And we have the transaction data, which is just a history of all the savings and refunds that customers have made using the app. Okay. And we have goal information, that is for what purpose the person is saving to us, what amount the person wants to, in the end, achieve. And also we have like the duration, how long would it take for this person to be able to achieve the goal that the person has set. And then we also have the app usage data set as to how frequently someone logs on the app and how long the person stays in a particular part of the app. And so that's just the app usage data set. So what don't we have? We don't have economic data. We don't have data on the income level of the customers, like what income are they earning? We don't have information on their expenditure. So we basically do not have any economic data of our customers. Now, so based on the data we have, we've come up with a way to define what potential investment is. So we just have data on the goals, right? And we assume that we set goals based on our capabilities as individuals. So if you set a goal, maybe you set a goal to be promoted next year, then it's based on the skills or things you know you can do. That's why you've set that goal. So we say that although we don't have data on the income and expenditure of the customers, we assume that whatever goal the customer sets, the customer has taken into consideration their level of income and their expenditure. So at the end of the day, net disposable income influences this goal. So in a way, we are saying that the goal amount gives us a fair idea of what the income the customer earns, okay, at the end of the day. So the potential investment value of a customer is therefore the probability that the customer will achieve this goal multiplied by the goal amount. So let's say if you set a goal of 10,000, we estimate the probability of you achieving this goal, and this value becomes your potential. Now, in the app, you can have multiple goals, like you can set different goals at a time. So at a point in time, a customer can have maybe like 5 goals running in the app. So we estimate the probability of each goal for each client, and then we sum that up. So it's more like the expected value of the customer considering all the individual goals. Now, how do we come up with this probability? We use the data we have, we use the demographic data, and then we use the transaction data and the goal data. So this is like the behavior of the customer over a period of time using this app. We use this data to build a model that would predict the probability of the customer achieving this goal. Now, so what we have is that we have a response variable, right? A customer will achieve a goal or not achieve a goal within the time frame that the customer has set. So we have that customer. We also have that customers can have multiple goals. So the data can be clustered. Our observations can be clustered per customer. So one customer can have like 5 goals, so that is in a cluster, and another customer can have just 1 goal, so that is also in another cluster, and so on. So now, what model can we use? Generally, if we have like independent observations, and our response variable is a non-normal response variable, like binary in our case, then we can use any generalized linear model like logistic regression to estimate the probability of achieving or not achieving. But in this case, we have this data set where a customer can have multiple goals. So in a way, our observations are in a cluster. So like you have the data set being the goals, like different goals, but these goals can be grouped per customer. So maybe a multiple of goals can belong to customer A, another multiple of goals can belong to customer B. So we expect that since it's the same customer setting multiple goals, there can be some dependency in this cluster. Let's say you pick a customer A. There can be some dependency because me saving towards maybe traveling to Asia and me saving towards my retirement, splitting the money could have some effect on achieving which goal first or not achieving which goal. So we expect that there would be some correlation among like the observation in one cluster. So then how do we model this? We can therefore use like a generalized linear mixed model. So basically what a generalized mixed model does is it adds a random effect to the model. And this random effect is supposed to capture the within cluster variations, like the correlations within each cluster. So this is the model, and this is just a link function. So this link function in our case would be a logic function. And X here is a set of design metrics for a set of predictors that I've already described, like the demographic data, the transaction data, the variables we would create from those data sets would be contained in X. And Z is just a design matrix for the random effects. Now, the B, which is a vector of random effects, the size of B is dependent on the number of clusters we have in our data set. So for instance, in this case, we are talking about customers. So if we have like 40,000 goals, but then the unique customers in that data set is about 20,000, then we would have a vector of 20,000 random effects. Now, the GLM, just like the generalized linear models, do not have a closed form solution. So what you do is you use a likelihood method to solve them. I'm not an expert, so I won't go into the details of how to solve this model. But what we used is the MATLAB implementation, which uses the restricted pseudo likelihood method. So that's what we use for estimating the various parameters, beta and then the and B. Now, like I said before, okay, let me go back here. Like I said before, the number of groups that you have in your data set determines the size of your B factor. Okay, so usually if the number of users, for instance, of group is very large, then you have this B factor. And then this also increases this integral. It increases the dimension of the integral. So what can we do? Can we in some way reduce the number of customers in a data set? So it's not like just randomly selecting customers, but we select customers so that if we build a model, we are able to generalize the model to unseen data. And the other is possibly we can use block CUR decomposition. So what block CUR does is that you have a matrix A. Let's say, for instance, so you have this part, you have each block in this. So this matrix A is made up of different blocks. Okay. So what you want to do is that instead of selecting maybe columns of A, you want to select blocks of A. Okay. So you, instead of selecting just, in our case, instead of selecting the goals, we want to select customers, representative customers with their goals. So that's what the block CUR does. And we've developed an algorithm that can do, like, for the normal CUR decomposition, develop an algorithm that can do that. So what we do is that we compute the singular vector decomposition of our data matrix. And then suppose that the rows are our observations, okay? If we want to select key rows, like representative rows of our data set, we take the left singular vector, and then for each singular vector, we pick the maximum value. So it's more like we are trying to determine the prominent rows in each singular vector. So if you pick, for instance, the first dominant singular vector in the matrix U, you just scroll through in absolute value, you pick the maximum value, and that is the prominent row. So that is the row that we perceive to be a representative of all the rows. Then you move on to the next singular vector. Now, to avoid picking the same indices every time, so for instance, if you pick in index 1 in the very first singular vector, to avoid picking the same index in the second singular vector, we project the second singular vector against the first singular vector, so that the entry in, let's say, the S vector you already picked. So if you pick index 1, so the entry in index 1 for the next singular vector would be zeroed out, so that if it's also dominant in there, because we've already picked it, we don't pick it again. So that's what this line of code does. So this is just projecting the subsequent singular vector against the previous one that you've already done to zero out the entries that you've already picked. Then after that, so this procedure can only pick up to k singular vectors. So if you have k singular vectors, you can only pick k indices. Now we would like to oversample. We would like to pick more than k singular indices. So how do you do it? We use an idea from leverage scores. So we compute the norm of the two norm of each row, and then we sort them in a decreasing order. So after sorting them in a decreasing order, we try to see, okay, the indices that we've already picked using step 1 and 2, if you still have them in the largest entry, take them out. So we take them out, and then the rest of the indices we would like to pick, if it's like maybe 3 more indices we would like to pick, we just pick the largest indices corresponding to the largest k-1 entries of L. So that's what the LDEM does. That's for the regular CUR, where you just pick rows. So this is not about the block. Now we modify this for the block. How do we do this? So we have a matrix A, and then this A has maybe G blocks in it, okay? And then the target rank we want is, for instance, K, okay? And then the desired number of groups we want to pick is T. So T is less than G, but T is greater than K, okay? Now, what we do is that first, for each group so we collect each group, and then we try to find the representative rows in the singular vector of each group. So for instance, after computing the singular vector of A, now for I belonging to like the group labels, so these are the distinct group labels, we first pick all the rows in U corresponding to this group. And then for each of the column vector in that U, we pick the maximum entry in absolute value. So we pick a representative row in the SAP U. So after picking this, we put them in U prime. So U prime would now be, so if we have, for instance, 40 groups, U prime would now be 40 by K. The dimension of U prime will now be 40 by K. And then after that, now, so U prime is more like group representatives. So you have user 1, user 2, user 3, or group 1, group 2, group 3. Now we would like to then select out of those groups a representative group. So so step 2 is like we select for each group a representative observation. Then step 3 is that after finding a representative for each group, we would like to select a representative group for the whole data set. So you just apply the LDIM that I described earlier to your U prime. And then the rows of A, the subsets of A, are now rows of A that are in block GS, where, sorry, this is supposed to be GT, where GT is just the subset of groups we've selected using the LDIM method. So, so now I will talk about the metric for segmentation. Okay, so after we've finished estimating the probability and estimating the potential value, how then do we identify who is like a customer who is underperforming or a customer who is overperforming? So the first one is that we take the potential value and then we divide it by the total. So the total is that, let's say if you have goal 1, 10,000, goal 2, 20,000, then the total of those two goals will be 20,000. And this potential is the potential value of all goals inclusive. So we divide it by the total. So that would be the potential investment value ratio. And then we just take the 25% percentile and then the 75 percentile. So the 25%, the lower quantile is just underperforming customer, and then the upper quantile is overperforming customers based on this ratio. Then the second metric is that, okay, customers save over time, right? So if I started saving in 2019, maybe 2020, I don't do anything, and then 2022, I do something. So what we want to do is that we would like ideally for the customer to be consistent. Okay, so you save every year. So what we try to do is we find your actual yearly investment value. So that means over the whole the total number of years you've been a customer, we take your portfolio value in the time that the data is collected, and then we divide it by the number of years you've been a customer. Then we also take the potential value that we've just estimated and divide it by the number of years since you've been a customer. So if your potential value, if your yearly potential value is greater than your yearly actual investment value, then you are underperforming. But then if it's less, if your potential value is less than what you are actually doing, then you are overperforming. So in the end, what we do is that the first metric, so we take people who are underperforming using the first metric, and then people who are underperforming using the second metric, and then we find the intersection. So we find the common people using the two metrics, and then we classify them as the low potential people. And then we do the same for the overperforming. We take the overperforming people using the first metric, and then the overperforming using the second metric. And then we classify them as high potential customers. So some results. So this is the statistics of the summary statistics of the data set. We have in the whole data set, we have 72,000 goals. And then this 72,000 goals is associated with 44,000 unique customers. Okay, so like I said before, in the GLM model, that means that we would have 44,000 random variables if we use all the customers. That is a very large model to build. Okay, and okay, then the active goals, these are goals that are still running. So we don't have any ground truth for them, are 38,000 out of the total number of goals. And then the closed and won goals are 16K, 16K approximately. So we see that this data set is balanced if we want to use the close. So the close and won are ground truth. We know that the customer has closed the goal or the customer has won the goal. So this is the ground truth. So this data set, the won and close data set, is what we'll use to build our GLM model. So we split this data into train, validation, and test data set. Now, here we see that some of the goals in our data set, we have customers who have multiple goals, like 14% of our customers have 2 goals, then 6% has 3 goals, 8% have more than 4 goals. So it is justifiable for us to use the generalized linear mixed model and not just a generalized linear model, because we indeed have some clusters in our data set. Then, so now we compare. Here we are just comparing, okay, if we use all the trained data set, that is, if we use all the customers, the 44 customers to build our model, so that we have like a 44,000 random effect. What is the performance of the model as compared to if we use the block CUR that I've described to reduce the number of customers that we input into the model, or that we use to train the model? So using all trained data sets, obviously we have like a higher accuracy as compared to using just 100 clients, for instance. But then we see that the time used, the computational time for using all these customers is higher than using just 10 clients. Okay, so we improve on the computational time significantly if we use like CUR, block CUR to select customers to train our model with. And the interesting thing is that what we are interested, because of our goal for the end, what we are interested in is we want to minimize the false positive rate. That is, we don't want the situation where somebody will not let's say achieve a goal, but we classify that person as somebody who will achieve the goal. So you notice that using this 100 client that has been selected by the CUR block gives us a lower false positive rate as compared to using the whole 44,000 clients. And the ROC curve is also not, I mean, it's equally good, though there is some variance, but then it's not that big of a difference. So you see that we don't deteriorate our the model performance that much. We increase computational time. We improve on the computational time significantly and still have good results using this CUR block method. And this is just a result on how we segment the customers. So the whole data set, we have that the average yearly potential in the whole data set is like, what we expect is 1,300 euros, approximately 1,300 euros. And realize that our high potential customers, after the segmentation, is very close to the average, okay? The average potential investment we expect from our high potential customers is very close to it. And they actually perform more than the average. So in a way, we can deduce that the metric we use to segment customers works well, at least for us. And we also notice that the low potential customers are people who are very young, and which is expected because I mean, young people do not actually usually have money to invest in mutual funds or anything of that. So, and then the high potential customers are people who are relatively old, like they've been working for a while, like generally people who might have like a good income level. So thank you for your attention. These are some references, and this is for more details on how the model for selecting the users, our model for selecting representative columns and rows, you can look at this paper, a hybrid dime and leverage scores based method for serials index selection. Thank you.
Thank you very much. Perfect. For your very nice presentation. I don't know if there is anyone on the audience that would like to make a question or make a comment. So maybe while people write on the chat or raise their hand, I can make a question about the segmentation of the clients. So you did this underperformance and overperformance based on this 25 and 75%.
Yeah.
Did your conclusions be sensitive to these thresholds if you increase it or decrease? So if you change this 25 and 75%, would your conclusions be very different or?
Oh, okay. So it wouldn't be very different because it would just lower the number of clients we have in the set. So for instance, if we lower the percentage, then we just have fewer clients, and then the intersection here might be low. So that's the only difference. So it's either expands or lowers it.
Okay, but the characterization of these groups would not change much.
Yeah, yeah.
Okay, thank you. So thank you very much. Well, people can still talk in the breakout rooms if you want to make additional questions or new questions. So let's move to the second speaker, which is Razul Taban. He is a PhD student of Instituto Superior Técnico and is also collaborating with CIF and SDG. And today he's going to speak about a novel balancing technique for mixed type variables based on SMOT. So, thank you very much.
Hello, everyone, and thanks from Professor Oliveira for introducing me. As Professor Oliveira mentioned, I will talk about a novel balancing technique for mixed type variable based on the SMOT. This work is done under supervision of Professor Oliveira and Professor Nunes from IST in University of Lisbon, and with the collaboration with our Serbian industrial partner, Center for Investment and Finance, under the supervision of Professor Miloš Bozovic. So let's start, or just, do you see my screen? Yeah.
Yes, yes, we see it clearly, and it is in full screen.
Yeah. Okay, great. So let's start our presentation with the question. All of you might work with the data and might heard about one of these topics, or probably work with the company or with the data set to find the credit defaulter, to find the fraud detection or disease, a kind of disease, which the question is that what is common in all of these problems? I will answer that we are willing to find a part of data, a part of observation, which is quite rare among them. For example, in credit default and fraud detection is less than 1% of the data set that we have. And this is quite hard task for the machine learning approaches to find it. So the rareness of the observation and the class that we are willing to correctly find them is the common characteristic in all of these problems. This called the imbalanced data problem, where the population of interest modeled as a mixture of random variables and have a very different probability of occurrence for the classes. One with very low number of observation, which we are calling a minority class, and the rest we call it majority class. And this funny cartoon shows the problem very well. Although the number of observations for the minority class is very, very low, but they are the population of our interest. We want to correctly learn them. They have much more importance for us. And this is quite a hard task for the machine learning approaches. And why it's so hard for them? Because the statistical modeling and machine learning are designed to minimize the misclassification error. They are designed to work with the balanced data set. And where the imbalanced data problem comes to the scene, make the task very hard for them, and leads to poor results, unsatisfactory classifier performance, and important issue of accuracy paradox, where, for example, if you imagine we have 90% of the observation for the majority class and 10% for the minority one, and we have the worst possible classifier, which assign the label majority to all the observation it will see in the future, you will probably reach the overall accuracy of 90%, which is quite good. But it's good when you have the balance set in the hand, not imbalanced data. So what would be the solution here? One solution is a balancing technique, which is quite famous in the area, and it's easy to apply to all the procedure that you have in your model. There are several different strategies, such as undersampling, which removes part of the data from majority class to reach a balanced set, or oversampling, which is introducing the new synthetic observation by the resampling techniques, or a hybrid one, which is a combination of both. Today, we will introduce a method under the area of oversampling, which wants to synthetically introduce new observation to reach a balanced set. Let's talk about a famous and usual approach in the area, which called the SMOTE. This is probably the most famous approach in the area, where it wants to synthetically introduce new observation. And how it works, it finds the k-nearest neighbors for all the minority observation using the Euclidean distance, where the minority class observation here shown with the circles, and then select the first parent among the minority observation with the equal probability of choosing. Then select the second parents among the k-nearest neighbors of the first parent, and then introduce a new observation, a synthetic one, using a convex combination of that selected parents, and the coefficient and the place that the new child would be placed comes from a realization of the uniform distribution. So simple, but it's very efficient, let's say like that. It shows a very good performance in different applications. But let's talk about the mixed type variable. When a data set coming from real world application, most of the times it has some categorical variables besides the numerical variables. We call it mixed type data set with mixed type variables. And the problem of the balancing technique is that they are not able to handle the data set with mixed type variables. They're mostly designed to work when the data and the variables are the numerical ones. When the data is mixed type variables, does have the mixed type variables, the solution in the area is to first, for example, ignore the categorical variables and then applying the balancing technique on that. But this leads to loss of information. We know that throwing away some part of the data that you will have, which is not very pleasant, is not very good approach. The other approach is encoding the categorical variables by the one-hot encoding or the other encoding, but this will lead to some problems. First, the course of dimensionality. For example, if you have several categorical variables and each categorical variable is a multi-level, for example, with 10, 12 different values, then you could imagine what happened to the data set that you have. It multiplied by 10 by 12 and introduced a lot of new variables. The scaling issue, for example, if you encode differently than one-hot encoding, which number should you assign to each class for that specific categorical variables, and what happened next when you apply the balancing technique. For example, imagine you have a binary variable and you perform the balancing technique on it and assume it's a numerical one, and then it will introduce new numbers between 0 and 1, which is not correct. We know that, and it would most of the times cause a very poor performance. And yet again, it would cause to ignore those variables. So the solution here would be the modification of SMOT in a way that it could handle this kind of problem when we have the mixed type variables. First modification should be regarding the distance or dissimilarity in the k-nearest neighbors algorithm. We should modify them in a way that it could find the k-nearest neighbors for mixed type variables. And the other modification is in the oversampling step and strategy. And the state of the art in this area is to use the majority vote among the labels for that categorical observation, to choose that instead of using the convex combination. And we keep this step like as a state of the art, and we change the distance similarity in our proposed approach. And the possible distances or dissimilarities in the area which are suggested by just two balancing techniques which exist. The first one is the SMOT NC, which is proposed by the original authors of the SMOT as a small part of their paper, and it could handle the nominal and the continuous variables like this. It calculates the distance in two different parts. The first part, like the Euclidean distance, which was similar to the normal case, and at the term, a penalty term, which calculate a distance like this. It multiply the simple matching with the coefficient. The simple matching says that if the label of that categorical variable is equal to each other, it gets 1, otherwise it gets 0. And it multiplied by that coefficient y, which they designed to take the median of the standard deviation, or the variance among the continuous or numerical variables. and then just sum up the distance altogether for each variable or each feature to calculate the distance. Other suggestion in the area comes with combining the smooth with the Gover dissimilarity coefficient. This is very interesting dissimilarity coefficient where Gover designed in a single equation like this, and it could handle the case of missing values and the case of mixed type variables. It calculates the case for the binary and the categorical with the simple matching, multiply with the coefficient delta, which get the value 1 when both of the observation that we are comparing to each other are exist and are not non-missing. If one or both is missing, it will get the 0, and the distance would get the 0 here. And for the numerical part, it calculates the difference between two absolute value of the difference between two variables, between two observation divided by the range of them. And by this, they will introduce a balancing technique which could handle the mixed type variable issue. And our novelty in this field is to combine this mode with the Huang dissimilarity. Huang dissimilarity is very similar to the previous dissimilarity, which is described with the authors of this mode. But the difference is the coefficient y, which it comes from the inspiration of the K-prototype clustering. They found the optimal value for that coefficient. They put the value of y like this. They get the number of numerical variable they have in the data set divided by 6 and multiplied by the median of that numerical variables. And by this, they calculate the dissimilarity of Huang dissimilarity. So we designed a new algorithm named mixed smooth like this. We get the data set, the data matrix, which is n times p, n for the number of the observation, p for the number of the variables or features that you have. And we just focus on the minority observation to introduce the synthetic observation. We first pick the first parent randomly among the minority class observation with the equal probability, and then finding its k-nearest neighbors using the Huang dissimilarity, and then selecting the second parents from the k-nearest neighbors of the first parent, and do the resampling step like this. We generate the new children such that for the numerical variables, we keep the things like original smooth as the convex combination of selected two parents, where the theta comes from the realization of the uniform distribution with the 0 mean and 1 variance. And if the variable is categorical, we use the mode of that categorical variable to choose the value for the children. And to show the result for our proposed approach, we pick a benchmark from the KL that I will introduce later. But the modeling procedure is like this. We run for 100 independent iterations the modeling to stay out of randomness in the results. We divide the data into the training and the test by the percentage of 70 to 30%. We apply the balancing technique, mixed smooth, on the training set. Then we train 3 different classifier: cart decision tree, random forest, and AdaBoost. And then we use the test set to assess the classifier performance and report the average of the performance measurements that we have. And for this evaluation metrics, we use the recall and the precision as the measure of the completeness and exactness, and use a new metric which named global metric. It calculate a metric using 3 terms of recall 1, recall 0, and precision 1. By this, we could find the perfect classifier. We consider all different aspects of the confusion matrix, and the value, the less value shows the best possible. Regarding the data set, we picked the heart disease prediction from UCI benchmark dataset, which has 13 different variables. One was ordered, the categorical ordered one, we exclude that one, but we kept the 6 numerical variables and 6 categorical ones, which consist 3 binary and 3 multi-class categorical variables. And the original observation ratio was 150 observation for the majority class and 120 observation for the minority. We know that this is not very imbalanced, so we synthetically forced to make the data set imbalanced data by removing some minority observation from the data set in each run. To reach the imbalance ratio equal to 8, which has 150 observation for the majority class and 36 observation for the minority one, and build a model. These are the results that we reached for them among different methods. The original shows the result when we use the original data without applying any balancing technique. The Gover shows the combination of the SMOT and the Gover dissimilarity. And the Huang is the method that we proposed here. In different rows, you could find the result for different classifiers. But when you compare the result of recall or precision for the original data to the balanced data, you could realize 10% increase in the recall, almost 10% in every balancing technique. The bold one shows the 2 best result that we reach. And to sum up and to compare our method with its competitor, which is Gover, if you compare in the metric recall 1 metric, you could realize that we did better. In the recall 0, we did better, and so on. And to say one word and compare in single metric, if you look into the global metrics, you could see the best result comes from the SMOT combination of the SMOT and Huang dissimilarity with the random forest, which shows the smallest value for the global metric. This proves that balancing technique could be a good solution here than keeping the original data. And also, it shows that our method could overperform the SMOT plus Gover dissimilarity. Although we will look into another dataset which comes from the real-world banking dataset in a collaboration with the CIF in Serbia. We received the dataset from a banking management which has 10 numerical and 10 categorical variables. We did some step before applying the balancing technique. We exclude those variables with more than 20% missing values, and we just injected or imputed the missing values with the median or mode of each variable within each class to prepare the data set before applying the balancing technique. And the analysis of that data set, which is oversampled using the balancing technique, shows that it could improve the information value of each feature or each variable by itself, and it could even improve or increase the average monotonicity among the features. This monotonicity shows a coefficient, a simple coefficient, which is 1 or -1, which is a rational one assigned to each variable by an expert in the field. For example, if the salary goes high, the probability of going into the default goes down, so it would have the -1 coefficient. And considering all possible combination of 4 input values, they constructed all possible models using the brute force approach. And it clearly shows that the balancing technique could lead to improvement of the quality of the constructed models, with the improvement in the Gini coefficient and pseudo R-square. And especially when we compare the mixed mode using the Huang dissimilarity to the smooth plus cover, we could see superiority in the Gini and R-square, which yet again shows our method could overperform the competitor of the smooth plus cover. And it also shows interesting result of 10% improvement in average for the Gini coefficient, and a huge improvement for the pseudo square, near 200% in average, comparing to the original data, which shows a big impact of the balancing technique in the real world data set. And it is very interesting to see that the method could work in the real data, not just in the synthetic and in the benchmarks. So to conclude that we present a balancing technique based on the famous approach of SMOD for the mixed type variables. It improved the classification performance, and also it avoided the curse of dimensionality and that loss of information problem, which is a usual solution in the field. And also we expanded the balancing technique to broader areas than the benchmarks, to the real world problems. And thank you for your attention. I will be very happy if there is any question that I could answer. Thank you.
Thank you very much, Khazoo. Any questions that anyone would like to raise to Khazoo? So once again, while people were thinking about possible questions, what I would like to ask you to comment is that there is a vast literature on the problem of balancing techniques for continuous random variables, but very few for this mixed type data. And it seems that doing something you could have, and this real program seems to point in that direction, could have a really improvement. You have any idea why people are not tackling these issues, or what are the difficulties in this problem?
Yes, the main difficulty comes from the calculation that distance metric, that there is not much distance or dissimilarity metric in the field that it could be used there. Just a few are in the hand, and probably it's too hard to design a new dissimilarity or distance metrics in the area. This is the thing that came to my mind regarding this issue.
Okay, thank you very much. So there is a question.
Yeah.
I don't know if you can read it. Should say, can we use this resulting method in sparse binary data where all variables are binary and more zeros in data?
It seems to be a kind of imbalanced data. If you have more zeros than one, probably. I believe that you could use the method, but I'm not sure about the performance of that. But it is interesting to see if it works and it could perform well. Yeah, that's a good question that I could imagine that if I could find a data set with this characteristic, it could be good to see how it would perform. Thank you.
You're welcome. So let me thank the three speakers of the session for their really interesting presentations, and let's go for the next session that Michiel will share.
Yeah, thank you, Rosario. Yeah, so thank you for all the past speakers. And now we move on to section 3, subpart 3 of our program, which is about optimization, a very important part of big math. So several of our PhD students deal with optimization to certain degrees. And we are very happy to have an expert as our first invited speaker, Professor Martinez. Professor Jose Mario Martinez is Emeritus Professor at Campinas State University in Sao Paulo, Brazil, since 3 years. And he dedicated his long and productive career to numerical optimization. And he made a lot of remarkable results that make him an internationally respected expert on various topics of nonlinear continuous optimization. So for instance, augmented Lagrangian methods, inexact restoration methods, spectral gradient methods, to which several of our PhD students have looked, constraint, qualification, and optimality conditions. And also very well fitted with this, with our big math project, is that Professor Martinez dedicated part of his research to optimizations together or with industrial relevance and interdisciplinary collaborations, for instance, with scientists from engineering, chemistry, and geology. So Professor Martinez has been awarded a National Order of Scientific Merit, which is awarded to Brazilian and foreign individuals in recognition of distinguished achievements. So that's great. And relevant contributions to science, technology, and innovation. And he's also a full member of the Brazilian Academy of Sciences since already 2009. So that would be already 12 years, 13 years. So Professor Martinez, are you able to share and to, yeah. I see your,
yes, I'm
yeah,
here.
we see you, we hear you.
Yes, okay.
And it's sunny. It seems sunny at your side.
Okay, thank you very much for your words, and I am very happy to be in this meeting. And I acknowledge that you invited me. So let me see if I can share the screen. Okay. Share. Okay.
Yeah, we see it.
Yeah, okay. So, well, I am going to talk about block coordinate search. It's a classical area of continuous optimization. This is a joint research with my colleague Ernesto Virgin. Ernesto Virgin is a professor in the University of São Paulo. I am a professor in the University of Campinas. Campinas is a city of the state of São Paulo. There is a state of São Paulo, and the city of São Paulo is the main city of the state, and Campinas is another important city of the state. So, okay, so let me begin with something about São Paulo, the city of São Paulo and its neighborhoods. I mean, the city of São Paulo is this one here. And it is divided into 96 neighborhoods. It is a very, very, very big city, the biggest city of South America, and I think the biggest city of the south of the world. And the problem that I am going to use for motivation is related with the city of São Paulo. So let me tell you that the University of São Paulo is here. Can you see my mouse, okay? You see? Yeah, the University of São Paulo is here, and my colleague Ernesto lives here, very close to the university. So the problem, the motivating problem that I am going to present consists of finding a trajectory, a route in the city of São Paulo that connects all the neighborhoods in such a way that the length of the trajectory is minimal, but where we don't know the station in each of the neighborhoods that connect the different points of the trajectory. That is to say, we need to determine both the sequence of neighborhoods and the points, the stations where a point, a station in each neighborhood that represent the vertices of the route that we want to determine, okay? So this is a motivating problem for our coordinate search strategy. And you observe that what we need to do, roughly speaking, is, well, roughly speaking, we have two problems. One is to establish the sequence of neighborhoods, and the other is to establish where the stations should be. So how to proceed? Assume that we have a given sequence of neighborhoods. So we are going to compute the length of the best trajectory that connect them, deciding the position of the stations. Then we have a function, the length, that depends on the chosen sequence. And we minimize this function, the function that goes from sequence to length. And the computation of the length depends on deciding the stations. And for minimizing this function, that is the global external function, we are going to use well-established traveling salesman techniques. But for computing each station that for minimizing the length, well, this is a continuous optimization problem. And for solving this continuous optimization problem that must be solved each time we need to evaluate the objective function, we are going to use coordinate search. Okay, so given a sequence of neighborhoods, we need to compute one station in each neighborhood, and this is continuous optimization. It is not discrete optimization. So it is natural to visit the neighborhood sequentially, updating the position of each station in order to decrease the total length. And this is coordinate search, block coordinate search, because if I visit one neighborhood at each moment, I am going to minimize the internal variables to the neighborhood, in this case, 2 variables for the 2 dimensions. And this is block coordinate search. Now, a neighborhood is not a traditional set. I mean, it is not a traditional set in the way we talk in general about sets in constraint optimization. Why? Because it is not a traditional set, because it is not clear, it is not described, naturally described by a set of equalities and inequalities. So as you are going to see, we need to decide another different way to describe this set, these sets that are the constraint sets for our problem. Okay, so in block coordinated set, at each iteration, one minimizes. This is general now. Now that I am not talking about the specific motivation problem that with which I began. At each iteration, one minimizes an approximation of the objective function with respect to a generally small set of variables, subject to constraints that corresponds to these variables. That is to say, we have constraints here. The unconstrained case and the case in which the constraints are simple, we are analyzed in the recent literature, in particular in a paper of our group. Here, I am going to address the problem in which block constraints, the constraints for each block, are not simple, and moreover, the case in which they are not defined by global sets of equations and inequations. I am going to present a general algorithm that minimizes quadratic models with quadratic regularization over blocks of variables. I am going to present convergence results and complexity results. In particular, given tolerance, delta, and epsilon for feasibility, complementarity, and optimality, I am going to show that a measure of criticality tends to 0, and the number of iterations and functional evaluations required to achieve criticality is of the order epsilon to the -2. What is really what can be expected for this type of problems? Okay. The structure of many practical problems suggests the employment of block coordinate descent method, BCD, for optimization. At each iteration of BCD, only a block of variables is modified with the purpose of obtaining sufficient decrease of the objective function. Although the coordinate descent paradigm is very natural and is implicitly used in different mathematical contexts, a classical example by Michael Powell many years ago showed that convergence results cannot be achieved under excessively naive implementations. We showed in a recent report that using sufficient descent based on regularization, the drawbacks represented by Powell's example can be removed. In that paper, we also showed that method based on high order regularization can be defined with convergence and worst-case complexity. However, the main results show that it is not worthwhile to use Taylor-like models of order greater than 2, because the complexity is dominated by the necessity of keeping consecutive iterations close enough. And this requirement is hard to achieve if models and regularizations are of high order. This is the reason why in the present research, I am going to restrict myself to quadratic models of the objective function and quadratic regularization. Okay, what I mean by non-standard feasible sets. This is a novelty of our approach here. I am going to consider a general feasible set for each block of variables. So at each iteration for BCD, we minimize a problem with probably a small number of variables that must satisfy some arbitrary constraints. But as I said before, the feasible set may not be defined by a global set of equalities and inequalities as usual in constraint optimization. Instead, equalities and inequalities that define the feasible set are going to be local in nature, in a sense that I am going to define below, making it possible more general domains than the ones defined by global equalities and inequalities. Formal presentation of the problem. Well, we want to minimize a function of n variables. The variables are divided in n blocks. And we are going to minimize this function subject to that xi is a block of variables, belongs to a specific constraint set for this block of variables. That is to say, we have a different constraint set omega I for each block of variables. The structure of the feasible sets. Now, here is the mysterious of the structure of the feasible set. The feasible sets are going to be closed and bounded. Moreover, for each feasible set, I am going to consider that each feasible set, each omega I, is contained in the union of some open sets. Such that on each of these open sets, the feasible set is represented by equalities and inequalities. But these equalities and inequalities are associated to the specific open set. I mean, we have a feasible set. I represent the feasible set. I consider the feasible set covered by a set of open sets. Inside of each open set, I can see this locally, and the feasible set inside of each open set is represented by some constraints that are associated to the open set. So the open sets for each open set are going to be said to be constitutive of omega I. Well, I am not going to consider equality constraints because, well, each equality constraints can be replaced by two inequalities. Anyway, I can consider explicitly equality constraints, and nothing is going to change essentially in what I am going to say now. Okay, this is a simple example where I show you a feasible set, not a very difficult one in this case, but it's just for representation. This red one is a typical feasible set. And you see that here I have several open sets, this round one, this rectangular one, this another round one, a rectangular one, and round one, and some circles and rectangles, and an interior one, okay? And the feasible set is contained in the union of the open sets. And if I restrict, the open sets are not disjoint, of course. And if I represent inside each open set, well, in this open set, I have different, for each open set, I have different representation with equalities and inequalities, with inequalities. In the block coordinate search method, at each iteration of BCD, given the current iterate, I choose one block, and I compute the following iteration, modifying only this block. So for computing the following iteration, I am going to approximate the minimization of the objective function, approximate the minimization of the objective function, subject to the fact that the corresponding block of variables belong to the corresponding feasible set, and the other variables are not modified. So I modify only one block of variables, the other ones stay fixed. And we do, I do an approximate minimization, not necessarily an exact minimization. Okay, so this is a more technical slide. How is exactly the BCD? Not exactly, but almost exactly the BCD, which are the main mathematical characteristics of the BCD. Well, I have some parameters of the algorithm, but the problem is the problem that I mentioned before. So now I am in one iteration. In this iteration, I choose one block of variables. I define an arbitrary Hessian approximation, not necessarily a Hessian, not necessarily a good approximation, maybe zero, maybe the identity, anything you want. And I find one of the feasible sets in which I represent what happens in this feasible set, and I find the new iterate in this feasible set, in this open, one of the open sets, I said, open set. The new iterate is in this open set that I find in some way. And in this open set, I compute something like a minimization of the quadratic approximation of the function, in the sense that the quadratic approximation of the function decreases with respect to the current approximation when regularized by a term, a regularizing term that defined by this regularization parameter sigma. And in addition to decreasing the quadratic approximation, I require the satisfaction, the fulfilling of approximate KKT condition, approximate approximality condition. Why approximate? Well, because I am not requiring that this KKT term is equal to 0, but only that it is smaller than a constant type the difference between two consecutive iterations. And here are the complementarity conditions. Well, this is the alternative one. It is the most interesting alternative. I have a second alternative that simply says that instead of, your problem is simple enough. I mean, it's simple enough so that instead of minimizing a quadratic approximation, you could try to minimize directly the objective function. I need to set this second alternative as well, even if from the theoretical point of view, is not interesting at all. The interesting part is here. I need to test a sufficient descent condition, and the sufficient descent condition is not enough that I need to decrease the objective function. I need to decrease the objective function minus a regularization term. Observe that this is different than the classical minimization, the classical sufficient descent conditions based on the so-called Armature type descent. Here I minimize, I require a minimization with respect to regularization. And this is a crucial point, because it is a crucial point that makes it possible that the second counterexample of Powell is not possible. This inhibits the second counterexample of Powell. From the theoretical point of view, alternative 2 is not necessary. Convergence and complexity theoretical results follow only with alternative 1. Alternative 2 was included because in many cases it is possible. Okay. The sufficient condition 10 is necessary, even in alternative 2. I mean, even if I minimize the true function, I need the sufficient descent condition. Maybe that the global minimizer of the true function is not good enough from the point of view of block coordinate descent. In fact, in the counterexample of Powell, he does exact minimization, but this is not good enough. Okay, and this is the reason. The reason is that the fulfillment of the descent function, of the sufficient descent function, implies that the difference between consecutive iteration tends to 0, and this feature is essential for the convergence of coordinate descent methods. Definition of criticality. Well, I am going to say that the point is critical in each, if there exists open set Aij, I is the block and J is the open set that I decide for this block, such that in all the blocks we have some kind of KKT conditions for the minimization of F restricted to the constitutive set, the constitutive constraints corresponding to the chosen open set and the corresponding block. Well, approximate, so with tolerance epsilon 0 and complementarity and feasibility hold for the same constraints with tolerance delta. I am going to prove, well, I am going to state that for given delta, the criticality, the algorithm tends to converge to critical points, and the number of iterations evaluation that are necessary to obtain criticality is of the order epsilon to the -2. For this, I need something like a Lipschitz assumption, restricted in some sense and so on, but okay, as a Lipschitz assumption with respect to gradients. Difference between gradients are of the order of the difference of the points, essentially is that. I need boundedness of the approximate or the Hessian approximations. I repeat, I don't need that they are Hessians. I don't need that they are Hessian approximations. I need simply that they are symmetric matrix and they are bounded. We are able to prove that each iteration is well defined. That is to say, given a point, we can find a point, we can find following the algorithm a point that satisfies the sufficient descent condition, and we can do this using this number, at most this number of increases of the regularization parameter, which means this number of evaluations of the function. Okay, this is the first lemma. Well, I also need that the objective function is bounded below. I need this almost cycling assumption. That is to say, I don't need to cycle over the different blocks and cycle 1, 2, 3, blah, 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 n, 1, 2, 3, and I can do something more chaotic, okay? Choose different blocks in chaotic order or something. But I need that for given m consecutive iterations, given a block I, and given m consecutive iteration, you are always going to find a modification of the block I. That is to say, even if I don't do the precise cycling between blocks 1 to n, 1 to n, okay, I can do something more liberal, but every maybe 100 iterations, all the blocks must be represented, okay? Well, using this, we can prove this essential result that says that difference between consecutive iteration goes to 0. I repeat that this is the property that is not satisfied by Powell's example. And we can prove that the number of iterations in which we can achieve that the difference between two consecutive iterations is smaller than epsilon is bounded by something of the order of epsilon to the -2. And then we have the arguments for convergence and complexity proofs. Okay, the arguments are this. Of course, I am not going to write the proof. According to BCD, at each iteration k, we select a block. And I optimize with respect to the variables of this block up to the approximate fulfillments of restricted KKT. This restricted KKT hold in one of the open sets that cover the choice, the omega chosen, and involve the constraints that are constitutive in this open set. However, the variables chosen now do not change during some less than m iteration. Therefore, during this iteration, and thanks to the ellipsis assumption, the approximate KKT condition that were satisfied in the chosen block are going to be satisfied approximately with the same open set and the same constitutive constraints used at iteration k. After this less than m iteration, the block I chosen is selected again, and the process is repeated. Since all the blocks are chosen infinitely many times in the way that I described below, approximate KKT conditions eventually are going to hold with respect to all the blocks, and we will be able to establish the number of iterations that we need for the fulfillment of KKT conditions up to any arbitrary precision. Okay, so this is the proof of this theorem that is stated here. What is stated here is essentially what I said in the proof. After, at most, an order of epsilon to the minus 2 iterations, I am going to find that the local KKT conditions, KKT optimality condition tends to 0, and that the number of iterations in which the local KKT condition of order approximated with epsilon do not hold is bounded away by this number here. Okay, is the number of iterations that I need for obtaining the approximate KKT condition, local KKT conditions, are of the order epsilon to the minus 2. In terms of function evaluations, is the same thing. That is to say, this is a complexity result corresponding to iterations. But in terms of functional evaluations, is the same thing because, as I said before, at each iteration, the number of function evaluations is a fixed number. It is not a number that depends on precision. So the total number of function evaluations is of the same order for obtaining optimality condition, is of the same order of the total number of iterations. And this order is epsilon to the minus 2. Okay, it is not reasonable to use models of higher order, because if I use model of higher order, I am going to obtain a higher order from the point of view of satisfaction the KKT condition, but I am not going to obtain a higher order from the point of view of putting the consecutive iteration together. So if I need epsilon to the minus 2 to put in the iterations close together, it is not worthwhile to employ more effort trying to satisfy the KKT condition with more precision. This is the reason. Okay, so solving the subproblems. Well, okay, this is something very technical. I mean, for solving the subproblems, I need a technical assumption that says what is written here. Okay, it is not very important. It's a technical assumption, and this is a picture that shows that in pathological situations, this technical assumption may not hold. I need an assumption on global minimizer, just because I consider that alternative true, that sometimes it is easy to obtain global minimizer in each block. So I need this assumption that for each block, if xi is a global minimizer, and then there exists j such that xi belongs to j and satisfy the KKT condition with respect to the constitutive constraints associated with aij. Okay, this is another technical assumption. And that's it. From the point of view, that's it. I mean, repeating, I have the algorithm, I have this almost cycling strategy. For each iteration of the algorithm, of the discrete algorithm, I need to solve a problem with BCD. I do this, and okay, and the algorithm is implemented that way. So in the experiments, I am going to use the example that I anticipated in the first slides. I mean, this problem that we define as the continuous version of the traveling salesman problem, TSP. So in this problem, the only difference with the traveling sales of the TSP is that for evaluating the function in the TSP, I am going to use the BCD method. I mean, from going to the algorithm for solving the TSP is only a heuristic algorithm. So I am going to go from one permutation to another permutation, and given a permutation, given a trajectory, a tentative trajectory for this the route, I need the BCD to find the station, the correct station. Now, the correct stations are used to define the objective function for the TSP. Okay, so, well, everybody knows what is the TSP. It's the famous problem in combinatorial optimization. We have P series with known pairwise distances, and given the problem consists in finding a permutation that minimizes the sum of the distances. In the present work, we consider a continuous variation with cities stations are not fixed, and therefore the pairwise are different. They're more precisely given the set of polygons omega 1, omega 2, omega p that may be non-convex. The problem consists of finding points xi such that minimizes the objective function. Okay, it's the same thing that I said before, okay? So given a permutation, the BCD is used to find a solution of this problem here. The BCD integrates, is part of the process of evaluating the metric function for a given permutation. So with this tool, constructive heuristics and neighborhood-based local searches are already developed for the classical TSP can be adapted to the problem. The discrete optimization strategy that I am going to use is a classical strategy in the TSP. It's a local search with an insertion-based neighborhood. The initial solution is a constructive heuristic based on insertions. The construction with initial permutation is a grid strategy. A typical iteration given a permutation I1, IP, and these associated points. Each point is removed and reinserted at all possible places, trying to decrease the objective function. But this is classical standard TSP. And for finding the optimal stations with BCD for a given permutation, we use the structure of the feasible sets. So, in each of the feasible sets, solving the problem has this form here. So we are able to use sigma equal to 0. Solving the problem is easy, computing intractable, and so on, and affordable. Compute the global minimizer is affordable. So we can use alternative 2. The global minimizer is going either in the segment AB intersected with omega, or is in the boundary omega, and this it makes it possible to solve globally the subproblem. Each segment of the boundary can be parameterized with a single variable, and the global minimizer is given by the best global minimizer among the global minimizer of these simple box constraint one-dimensional problems. Okay. So the global minimizer of each box constrained one-dimensional problem can be computed up to any desired precision. And if multiple solutions exist, in order to increase the chance of satisfying the sufficient descent condition, the closest one to X to the present point would be preferred. So let me go to the computational experiments. So we implemented the discrete optimization strategy, that is to say the TSP insertion-based strategy with the BCD method to compute the function value. I used the cyclic strategy. The methods were implemented in Fortran and so on. Okay. São Paulo again. So the city of São Paulo is a big city, 5 million square kilometers of extension, more than 12 million people. Is the most populous city in Brazil, America, the Portuguese-speaking countries, and the entire southern hemisphere. It is divided into regions, and each region is divided into districts. Then the districts are divided into neighborhoods, and we talk about neighborhoods. The city has a total of 96 neighborhoods, so the considered problem consists in finding the shortest route to visit all of them. Okay, so here again, you know it. This is the city of São Paulo, this very, very big city. These are the neighborhoods. And these are the TSP iterations of the methods. So observe that we begin here, we have 0 iteration. In the 0 iteration, the length of the route is 230 kilometers, okay? A big city, no? We have routes of 200 kilometers inside the city, you know? And this is the number of, for each iteration, TSP iteration. This is the number of calls to BCD that we need. And this is the number of cycles of the BCD. So these all numbers are computed. Are computed here. We arrive to a reasonable solution in 51 TSP iterations. The solution has 212 kilometers, and well, reading the solution is what I already said. Oh, the important thing is that all this problem used essentially 1 hour of CPU time. Okay, all this is 1 hour. This is the evolution of the length of the trajectory along iterations, well, almost linear degrees, something like this. And these are some of the generated routes. So here I have a route with 230 kilometers, 276 kilometers, 274 kilometers. And here is the solution with 212 kilometers. So this route that you see here inside a single city, the city of São Paulo, has 212 kilometers. This is a kind of a zoom of the route. Goes from here to here to here to here to here to here, visiting all the neighborhoods very carefully. Okay, conclusions. As I said before, the framework presented in the present work can be extended in order to consider Taylor-like high-order models satisfying well-established regularity assumption. This can be done. It has been done. But I wonder that theoretical results and practical results too reveal that in this case, using high-order models associated with coordinate descents is not worthwhile. It is not worthwhile to use more than models of order 2. The reason is that overall computed work is dominated by the necessity of obtaining fast decrease of the distance between consecutive iterates, whereas high-order models do not help for achieving such purpose. On the contrary, they seem to put successive iterates far away one from the other. More interesting from the practical point of view is the possibility of exploit the particular case in which the constraints that define each omega may be expressed in the form of global equality of inequality. This should be the more classical case. Of course, this is a particular case of the one addressed here that corresponds to the fact that we have only one open set for each neighborhood, for each block. In this case, the obvious choice for solving subproblems consists of using some well-established constraint optimization software. From the theoretical point of view, there is nothing to be added, since practical optimization methods for constraint optimization may fail or not for different reasons, leading to perhaps abrupt interruption of the broad optimization. However, in many practical cases should be useful. Finally, the reasons why we consider feasible set omega with the local constraint structure defined as open covering sets and constitutive constraints is not strictly related to block coordinate methods. In fact, in contact with several practical problems, you can find situations where the reasonable representation of constraints is not the global one. I mean, you need represent the constraints of one way in one region, other way in other region, and so on. So I believe that different approaches than the one suggested here are possible, most of them motivated by the particular structure of the practical problem at hand. Okay, that's it. If you want to see the paper related to this talk, the paper is not published yet, and you can find it here in this archive, in the archive collection. Okay, so 45 minutes, it's okay. Okay.
Thank you, Professor Martinez. Great talk.
Very much.
Very fascinating, interesting on a timely topic. So how long would it actually take you to do that trip in terms of time?
No, because I don't live in São Paulo, and during I don't live in the city of São Paulo. And I think my colleague Ernesto Virgin did it. During the pandemic, I didn't travel very much to São Paulo, neither to São Paulo, neither to any other place. So
yeah.
To São Paulo.
So, but with all the busy traffic, it would take a long time, I guess.
Certainly, yeah.
So if there are any questions from the audience, you can type in the chat or just unmute, I guess. In the meantime, I have several questions, in fact. So, there's a question from our Giovanni Naldi. Yes, you can unmute, please.
Yes, thank you for your beautiful lecture. I'm Giovanni Naldi, University of Milano. I apologize, probably I missed some detail, but for example, for the application TSP, if there is some stopping criteria, I mean, I miss if there is some stopping criteria in order to stop the iterations.
No, it was stopped by the difference between two consecutive iterations, the TSP. The BCD, no, the BCD has its own stopping criteria, but the TSP, the global TSP, difference between consecutive iterations.
Okay, thank you.
Okay, so you said something about the more chaotic orders of blocks that makes one think of randomized choices. Would you recommend this versus deterministic strategies?
I mean, we tried. I mean, we did some experiments with random. I mean, safeguarded, of course, because I need this to be all the blocks to be represented in. But in this problem, there was not any improvement.
No real advances.
No, we are confident that in fact random choices are promising, but it doesn't seem to be in this problem.
And you need, for the theory, you need this safeguarded. You cannot cope with truly random strategies, right?
Well, not in the present. Not up to now. I need a safeguard.
Yeah. You wrote several papers about inexact methods throughout your long career and productive career. So is there anything, do you have any recommendations on like how well you should solve this you said about approximately solving. What is the balance between approximately solving and versus the cost in time of iterations? Is that easy to say, or is that a hard question?
It is not. In fact, it is not easy to say. I mean, you can find problems where, I mean, only one iteration of SQP type quadratic approximation and so on is enough, and this is the best thing to do. And in other situations, maybe you need more iterations, and I think this is quite problem dependent. I could not risk a general opinion.
Okay. If there are no more questions, maybe we can ask Professor Martinez to stay around and be in the breakout rooms if you can, and because several of our PhD students work with optimization problems and methods, so maybe they are very interested in chatting with you. Okay.
Thank you very much. I will be here. Yes.
Yes. So we have a break until 16:42 to add some safeguard. Alessandra, would you like to?
Okay. So I think the speaker can go if they want to the breaking rooms to have additional discussions during the break. Okay. And we reconvene in half an hour, essentially. Okay.
And thank you again.